Yeah, cams on everyone. There'll be no break on today. So in case someone needs to use restroom or something, you can go and come back. Not an issue. Then let's see. So last class we have finished with variable mass system, rotational center of mass. Rotational mechanics has a pretty good weightage in advanced, right? Every year you get at least 2 to 3 questions. Chapter is not tough. The thing is, like, all the previous chapters do pop up again. So if you're decent with the other chapters, it shouldn't be that difficult. The only new part will be angular momentum that we will see. So let's start off. So first thing, we'll start off with a rigid body. We did have a little discussion on this in rigid body constraints. So what's a rigid body? In a rigid body, the distance between two points is constant. Simple definition, but quite a powerful statement here. What it means is, no matter what you do, you cannot change the distance between 2 points. That means body cannot be deformed. You cannot compress it. You cannot elongate it. Now, tell me one thing. Let's say if I'm here at rest and you are there here, and I'm telling you distance between you and me is fixed. But I'm also telling you that you're moving. How is that possible? Let's say I tie you, we both are tied with a rod. Okay, I'm fixed, I can't move. The rod cannot stretch, rod cannot compress. But I'm saying you can move, you're moving. How is that possible? The only way that you can move by keeping the distance same is if you go in a circle, isn't it? That is the only possibility you have, because you can't go away from me, you can't come near to me, you will keep being tangential, you'll go in a circle. So in a rigid body, since the distance is constant, the only way one point can move with respect to another is in a circle. That means if you take some random rigid body here, and if this is point A, and if you say B is going in a circle here, so A will think B is going in this circle. If you ask about C, A will think C is going in this circle. So literally every point on the body will think every other point is going in a circle. You're getting it? If you ask about C, C will think B is going in a circle. You're getting it? Every point will think every other point is going in a circle. A thinks B and C are going in circle. Now, if you extend this further, forget about a point, if you take even any line also. So if you take any random body there, and if you draw a random line AB, and if you draw another line CD, if you say line AB rotates by theta, you can be sure line CD also rotates by theta. Why? Think about it. If I join the points A, B, C, D, won't I get a quadrilateral? So if I rotate one side, To maintain the same shape, every side should rotate same angle, isn't it? Because distance between 2 points does not change. That means on a rigid body, every line rotates by same theta. So you connect any 2 points, all lines rotate by same angle. That is, all lines have same angular velocity. So you can make a statement there. We can say all the lines on the rigid body have same angular velocity. This is called angular velocity of the body. Now we learned about angular velocity in circular motion. That and this are completely different. Angular velocity of a body is different from angular velocity of a particle. I'll show you what it means. But have a look at this. Again, I'm not teaching you anything new. We are simply playing with this rigid body concept. Clear, everyone? Missing. So the usual form is this. So if you have a rigid body, so if you take this line AB, and if you say this line is rotating with omega, I can take another random line CD, and you can say this line is rotating with omega. So omega with respect to omega of a point with respect to any point on the rigid body is same. It is constant. So angular velocity of a body is constant. Then what is the angular velocity we studied in circular motion? What we studied in circular motion was something else. That's angular velocity of a particle. Do you remember last time when I taught you in center of mass, circular motion is different from rotational motion. Circular motion is defined for particles. Rotational motion is defined for bodies. Body is a cluster of particles. Translation motion is defined for bodies. Linear motion, the particle motion, that's a what do you call it? A linear motion or 1D motion is for particles. So don't get confused between angular velocity of a particle and angular velocity of a body. For example, if you have a particle going in a circle, we have done this question. If this angle is theta, this angle is theta by 2. So consider a particle going in a circle. Radius r with speed u. So if you remember, if you ask, oh, what is the angular velocity? It will say u by r, d theta by dt. But if you ask a, what is the angular velocity? It will say d theta by 2 dt, which is u by 2r. Did you see? Depending on who is watching, angular velocity of the particle changes. So angular velocity of a particle depends on the observer. Angular velocity of the body doesn't depend on who is the observer on the rigid body. Particle depends on observer. So there, that's a difference between angular velocity of a particle and angular velocity of a body. If someone says the body is rotating with omega, the body is rotating with omega, done. You need not ask, sir, about which axis. Go and stand anywhere on the body, you will see it as same omega. But if I say the particle is rotating with omega, then you need to tell me, okay, about which axis? I hope you're getting the difference. Particle, body, completely different. I hope you see, remember this question from circular motion. Right? Yeah, so the whole concept of this thing is that if you go and stand on a rigid body and if you look at one point, you see omega. You go and stand anywhere point, any other point and look at any other point, you'll see still see omega. Clear? That's it. That is the main concept there. Let's see a question based on this, how they can frame on it. Let's say top view. We have a disk. The radius is 1 meter. This point is A, this point is B. B is going this way with 2 meters per second. And A ka velocity is towards B. This is the center O. So VB is 2 meter per second. J cap. VA bar is along line AB. This much information you have. Now you might have a doubt like, sir, how is this kind of velocities possible? These kind of velocities are possible, when the coin is going and rotating. That means this coin is actually rotating and translating. You're getting how it is? It is spinning also, it is translating also. In such kind of motions, you can get these kind of velocities. Getting it? So these are the velocities at this instant. At this instant, these are the velocities at this instant. So find velocity of A, omega of the disk, and velocity of the center O at this instant. It's a rigid disk. There's much information you have. You know velocity of one point and you know velocity of A is towards B. Using this info, can you find velocity of A, omega of the disk, and the velocity of the center? It will be a good, advanced में more than one choice question. Give it a try, take a minute, then I'll show you a few points. And then I'll ask you one more like this. You can find VA. Do you remember on a rigid body, velocity along the line joining must be same. So it's a rigid body constraint. It has nothing to do with what I taught you today. नहीं Daksha. Let me help you with one question. See, again, most of the stuff, right? You already learned. It's not like it is something new. Let me just don't draw this. So this is the disk. You need to ask yourself, okay, this is a rigid body. This is point A. This was point B. So if I draw the line joining them, look at the velocities. So this was 2 meter per second. This angle was 45 degrees. So if you look at the components, this will be 2 sine 45 and this will be 2 cos 45. And this is velocity VA. You remember, for a rigid body, the velocity along the line joining must be same. If it is not same, what will happen? The rod will either stretch or compress. We have done this in NLM, in rigid body constraint. There. Remember this? So on a rigid body, if you take 2 points, you can take the velocities along the line and perpendicular. If the velocity VA is greater than VB, rod elongates, lesser it will compress. So they have to be equal. This is page 46 NLM. So velocity along line AB must be same because it's a rigid body. Therefore, we'll get VA is equal to 2 cos 45 there, which is 1 by root 2. You want the vector form? Vector form will be minus I cap plus J cap by 2, isn't it? 1 by root 2 cos 45, 1 by root 2 sine 45, I cap and J cap. That's your velocity at A. What about omega? This I taught you in circular motion. Who is responsible for rotation? This guy is your V tangential. Velocity perpendicular to the line joining by distance between them. So in this case, it is 2 sine 45 by distance between them is r root 2. R is 1, so omega is 1 radian per second. And what about the direction? So if you just look at the rod, this is how it is looking. This was B, this was A, this was 2 sine 45. So you're rotating this way, clockwise. So omega was 1 radian per second. Where did you see this thing? This thing came from circular motion, page 17. We have already done this last time also, if you remember. If you have 2 points and if you know their velocities, resolve the velocities perpendicular to the line joining and take relative by distance between them. This is page 17, circular motion. There, you got omega also. Now we need to find the velocity of the center. There, till now I didn't teach you anything new, right? These both you know from circular motion and NLM. How do you think we should proceed for center? Think, I'll give you a minute. Right, Purusa, you got it. Listen, the idea is simple. Just now we proved that no matter where you stand, and if you look at everyone, you think everyone is going with same omega. And just now we calculated omega of the disk is 1 radian per second clockwise. So let's go and stand on point B. So if you stand on point B and if you look at the center C, what will B think about C? It goes in a circle. Agreed? That is the whole story. So B thinks C is going in a circle like this. Which way? Clockwise rotation. So this way. With what velocity? R omega. So B thinks C is going in a circle. With omega 1 radian per second clockwise. You're done. So velocity of C as seen by B is minus r omega I cap. R is 1, omega is 1. So velocity of C with respect to ground frame is velocity of C with respect to B plus velocity of B with respect to ground. This is minus I cap and B is going in the vertical direction in this thing. Right. So if you try to, so if you actually see the motion, this is how the motion is going. So this disk is going this way with a speed of minus I plus 2j, and it is rotating with omega 1 radian per second. Like I showed you before. So this was actually going like this. This is how this disk is going. It's rotating also and it's translating in the third quadrant. Use na Vihan. Use and get the answer. You'll get it. This is faster. So, Ahana, did you get it? You can't be root 2. 2 sine 45 is how much? You're right. I made a mistake. Root 2. Then how much is this? Minus I plus j. Yeah, you're right. I did a mistake. VA is minus I plus j. Clear with this thing? Everyone got the process? So this is faster, nothing else. Like Vihan saying, you could have used rigid body constant also. You can say Vx, Vy, and solve, but this gives you answer a little faster. Let's see one more. All got this? Second one, similar question. We have a square plate. Side is 1 meter. A is going like this, 2 meter per second, 45 degrees. B is going like this. So velocity of B is towards A. C is the center. Find velocity, find omega of the thing, find omega of the plate and the velocity of the center. Same thing, I just changed the shape. Carried, I leave it 2 minutes. Idea is the same. Okay. Get the center का velocity. Omega must be how much? Omega is root 2. Velocity of center is. Can you give me an I cap and J cap vector form? Okay. Let's see. So if you resolve this velocity into components, this will be 2 cos 45. This is 2 sine 45. This is your velocity of P. We don't need VB, but I can find actually. So VB will be 2 sine 45 j cap. Omega will be 2 cos 45 by distance is 1 meter, which is root 2, right? Radians per second. That is also clockwise. This is the center, right? So what I will do, I'll stand on B and look at center C. You can stand at A also. You can do it multiple ways. There's nothing like one is right and one is wrong. So if I just go and stand at the center here, B, I will think this guy is going in a circle where this radius R will be half of the diagonal, which is 1 by root 2. So this guy ka speed will be R omega. Agreed? And this angle will be how much? 45. R is 1 by root 2, omega is root 2, so that is 1 meter per second. So velocity of center as seen by B. So B thinks velocity of center is cos 45 I cap minus sine 45 j cap. So 1 by root 2 I cap minus j cap. So velocity of the center with respect to ground is velocity of center with respect to B plus velocity of B with respect to ground. So 1 by root 2 I minus j, and B ka velocity is root 2 j cap. Bring all j caps together. That is 1 by root 2 minus 1 by root 2, 2 minus 1. So yeah, 1 by root 2 I plus j. Right? You can add that and see. You will get the root 2 minus 1 by root 2. Root 2 minus 1 by root 2. So that is 1 by root 2. This is the velocity of the center C. You have to add the B velocity na? With respect to B, it is 1 meter per second. Is this clear, everyone? So once you find omega, you can just stand on a point whose velocity you know, and then find that rotation and just add it back. You could have, stood on A also and solved the problem. You would have got the same answer. If we calculate with respect to A, we get velocity of C. Fine, na? Then add A velocity back, na? God. You have to add A velocity also, na? Ground frame में चाहिए आपको. That will take care. Is this clear, everyone? So there, these are one kind of problems based on your rigid body constraint, circular motion, and the property that, no matter where you stand, you will think the other guy is going with omega. Make sense? Devika, your cam is blank, right? Next one. So this thing is just a concept there. Useful one. Now in rotational mechanics, right? Primarily, there are three main concepts. One is the calculation of torque. Second is moment of inertia. Third is no slipping condition. If you know these three things, 80% of the chapter is in your hands. Just like if you remember when we did NLM, we did constraints, we did FBDs. If you know these two things, the entire NLM was easy, isn't it? So the major problem that I see when people study rotation, right, they don't do things in a systematic way. They're not strong in each part, right? They try to mix up everything at the same time and they make a khichdi out of it. So when the problem comes, they really don't know how to proceed with this. Like, the way we do every time, the steps to solve a problem. When something is tough, divide it into as many small parts as possible and then try to study each part. That's how it works. It's like when you want to improve something, right? People all think about big things. That doesn't work. You take out the whole thing, divide it into all subparts, and then try to improve each subpart. There's an example. This England bicycle team, na? England ka race ka cycling team, right? They have never won a championship. I think I don't remember the dates clearly, but I think till 1980s or 70s, they have never won a championship. They always used to come in like, last place or last but one place, completely gone. So then they hired a coach for a cycling coach, right, for this England team and said, yeah, dekhte kya hoga, meaning they didn't have really big hopes, but this guy was a pretty strict master. First thing what he did, he comes there, he sees everything, and then, he gets the routine, everything properly. And it's not like, the England team, cycle team was lazy people. They're sincere and all, but nothing is there proper. So this guy from day one, right? Everything. Morning, okay, cycle tires are checked. How is your health? Are you running properly? Are you eating properly? What are you eating? What time do you sleep? Right? When you run on the treadmill, what speed you run? Matlab, literally, this guy calculated each and every data for each person. Right? They had so much data on each athlete and each person. And when you're cycling, what is your this thing on this day? How do you behave? This guy literally did everything. And they started working on each small thing. I think 2 years later, they won 6 years in a row, the national championship. 6 years in a row. They were the champions. You should read about that. So the strategy comes from that. If a system has 10 parts, take out all the 10 parts and work on each part separately, and the overall thing will improve. Even when you're studying, you should do the same thing. A problem is we try to think like, we will do big things and suddenly we'll get a huge improvement. Doesn't work that way. The next one is torque. So torque, that is a symbol I write. Maybe I think in some books it is written something like this. I don't know what it is. So I write like this. So that is torque. So what is torque? A body continues to be in a state of rest or uniform rotation. We have written a same definition in Newton's first law for force. A body continues to be rest in uniform motion until unless a force is applied on it. So here we will write for uniform rotation. So force is something that is required to translate a body. Torque is something that is required to rotate a body. Simply keep that in mind. That's it. That is the main theme there. Until and unless torque is applied. So if you want to rotate a body, you need to apply torque, not force. Torque depends on force, but force is not same as torque. Right. Now, before jumping into it, we need to define something else called axis of rotation. Now, in translation, when I say applied a force, you applied a force. There is no discussion. It is fine. But torque is not like that. We need to define something called axis of rotation. What is axis of rotation? For example, if you take a rigid body here, and let's say this is rotating with some angular velocity. Now, if you take different points here, now this point is going in this circle. If you take this point here, this guy is going in this circle. If you take this point here, this guy is going in this circle. So each point is going in different circles. But if you notice something, the particles go in different circles. But if you look at the center of all the circles, they lie on a line. The particles on a rotating body go in different circles, and the line joining the centers of the circles is the axis of rotation. Best example is your door. When you rotate your door, when you open your door or close your door, every point on the door is going in a circle. And when you take that circle ka center, they will lie on that hinge. The center of these circles is called the axis of rotation. Able to visualize your door? So if you take your door here like this, This is your axis of rotation. That is how we represent an axis, a line with that circular thing. So if you look at the points here, this point is going in this circle, this point is going in this circle, everyone is going in different circles, right? Another example is your ceiling fan. If you look at your ceiling fan, you have the three blades or whatever. This would be the axis of rotation. So everyone is going in circles here. So this is your axis of rotation. So this thing is similar to actually 1D motion. You're rotating in one plane. Ever seen a top rotating? Top rotates about itself, and top also rotates, in a pretty weird way. That's like it's a double rotation. So, like for example, see if you look at this book here, this black line is there. Now this is like your hinge. So when I try to rotate this book, you can clearly see every point on the book, right, will go in a circle, and that circle center will lie on this black line. You're getting it? So basically, this is called axis of rotation. There is an axis there, and it is rotating about it. But there is something even more fundamental. We call it point of rotation. Is this page clear, everyone? So point of rotation, this is like 3D. You can rotate about multiple axes of rotation. It is a combination of axis of rotations. Meaning, for example, see the same book, if I take like this, see, now I'm holding like this, like a claw. I can rotate this way. I can rotate front and back. I can rotate like this also, no? You're getting it? There are multiple axes of rotations. That same book, see, I can rotate it left and right. How is the axis of rotation now? Into the plane, isn't it? It is rotating about this thing. If I rotate this way, then what is the axis of rotation? Perpendicular. You're getting it? If I rotate this way, then this one. You can see there are three axes of rotations. So point of rotation is like three one-dimensional, or you can say three axes of rotations. Another best example is your shoulder. When you look at your shoulder, right? Look at your shoulder, how it can go. Your shoulder can go left and right. Your shoulder can go front and back. Your shoulder can also go this way, right? So there are three axes of rotations for your shoulder also. Your shoulder is a point of rotation. It is restricted in a bit, but it can actually, technically speaking, it can go in three directions. It can have three rotations. So an axis of rotation, point of rotation is like one axis of rotations. So X, Y, Z if you take. So if you have a disk like this, and let's say this is rotating like this, and this disk itself is rotating like this. You're getting how it is? Like top basically. If you look at the top rotating anytime, the top will rotate about its axis, and the top itself is rotating like this. You have two axes of rotations. I hope you're able to visualize the top. I hope everyone is getting right. What is the difference between point of rotation and axis of rotation? So example, the book is a good one. You can just catch the book like this, and you can see there are multiple. That's a point of rotation. Your shoulder is another good example. So if we take rotation about the shoulder, so here shoulder is point of rotation. So if you have a person here, let's say, so this is your hand and this is how you're rotating. How is the axis of rotation? The axis of rotation will be like this, isn't it? So axis of rotation in y-axis, and this circle is going in xz plane. Make sense? It is rotating in XZ plane. So here you can see this thing. It is rotating in XZ plane, but the axis is in Y direction. Suppose if you are rotating your hand like this, keep it straight and rotate like this. Means now you're rotating in XY plane, and the axis of rotation is into the plane, Z axis. Means it is like this in front of you. Third one, he can rotate like this. This would be YZ plane. And your axis of rotation is X axis. I hope everyone is able to visualize. So axis of rotation is perpendicular to the plane of rotation. So if you're rotating in XY plane, the axis will be out of the plane, just like it's like a pseudo vector. We use right hand thumb rule. So axis of rotation is perpendicular to the plane of rotation. Is this making sense, everyone? This we had a discussion there in pseudo vector and all in circular motion. So basically what this means is, if someone tells you tomorrow torque is equal to 20 Newton meter K cap. So what they're telling you is indirectly, this is the direction of the thumb. And the curl of the fingers gives you the rotation of the body. So all quantities in this rotation, right, are pseudo vectors. Hope you remember this. This is the third time we are discussing this. First time was in vectors, and then we did this in circular motion also. The right hand thumb rule. So basically, this is your torque ka direction, and this is your rotation ka direction, the fingers. This is a pseudo vector. The K cap doesn't give you the actual direction, it gives you the sense of rotation. So the K cap implies so thumb is like this K cap. So it is like this. So put your thumb out of the plane and then rotate, isn't it? This gives you the rotation. Thumb will give the direction. If the thumb is downward, put your thumb down and then rotate this way. So rotation is this way. Make sense? So there, that is about axis of rotation and point of rotation. Generally, we study axis of rotation because if you know axis of rotation, point of rotation is like, like I said, 3D. You can split that into 3 axes of rotation and study them separately. Any doubt so far? Clear? Arnav, Arya, Devansh, Jainil, Ojas. Now, how to calculate this torque? Now, this is completely experimental. Have a look at this. Next thing. So, experimentally, when we try to find this torque, we have cases. Case 1. So, this is your axis of rotation. Let's say we have a rod or something here. So, you are applying a force such that the force is passing through the axis. And what do we observe? We observe there's no rotation. You can try this, meaning, see, if I take this book here and if I try to apply force like this, ab kitna bhi push karo, it will not rotate. It will move maybe, but it will not rotate. If you apply force exactly on the hinge, right, you cannot rotate your door. So if the force passes through the axis of rotation, there is no torque. We observe there is no rotation. So torque is 0. Case 2. Let's say you are applying a force F here, perpendicular to the rod and in the plane. And if you take this distance to be r, again, experimentally, people found out the torque is proportional to r and torque is proportional to f. Torque is equal to rf. And again, you can try with the door, Suppose if this was the door again, if you try to go and apply force here near the hinge and try to push, it is more difficult. The farther you are from the hinge, it is more easy to rotate the door. So more distance, more easy to rotate. Again, like I said, it's all experimental stuff. We still didn't get the final formula though. Clear? Then case 3, you are applying a force F at an angle theta. This is your r bar, the distance from there. Now this can be split into two parts. You can split this into two parts, where one component is F cos theta, and you can clearly see it is passing through the axis. This is your case 1. The torque is 0. The second one is your F sine theta. This is perpendicular to the axis. This is your case 2. So here the torque is r into F sine theta. So the actual torque is only due to the perpendicular component. So your formula comes out to be torque is equal to rf sine theta. If you write this in the vector form, torque is equal to r bar cross f bar. Now here, the important thing is this. What is r bar? R bar is a vector. It's not the position vector. It's a r bar is a vector from the axis to the point where the force is applied. Quite an important thing. So there, this is your final formula for torque. It's a cross product. It's a pseudo vector. Cross products are pseudo vectors, remember? They are always out of the plane. R bar is not the position vector. R bar is a vector from the point axis of rotation to the point where you apply the force. Have a look at this. Clear? Now, when you want to calculate, every time you want to do this cross product and stuff, there is a much better way to calculate for problems. Now see, go ahead. Any doubts? Arush? Ansh, clear? No. So this thing which we have, listen carefully. If you got this, the same thing will apply again for angular momentum also. And this thing keeps going. What I'm teaching you now will keep coming everywhere wherever there's a cross product. So I can write this thing as r into f sine theta. Now the meaning of this is, if you have a force F, this is your r bar, this is your axis. If you extend the vector and angle theta, you can resolve the velocity into two components, F force into components F cos theta. This is your parallel component. This is your F sine theta. This is your perpendicular component. So we can clearly see torque is R into F perpendicular. The parallel component is useless. It passes through the axis. So instead of writing R cross F, you can always write R into F perpendicular. So what you need to do is simply, whenever you have a force, resolve into components and take the perpendicular and multiply with the distance. Or there's another way you can write. You can also write this thing as Rf sine theta is R sine theta into F. This is the one which we will use most of the time. 90% of the time I have seen the second one comes. So if you have a force F, and let's say this is your R bar and this is your axis, extend the vector theta. So what we do here, extend the force vector, then drop the perpendicular. This is also theta. This will be R sine theta, which is R perpendicular. So torque can also be written as perpendicular distance into force. Don't mess with the force. Let the force be as it is. Just extend the force vector and drop a perpendicular. This one we use a lot. Extend the force vector and drop a perpendicular. Both are right. You can use any one of them, your convenience. You will see when you do few problems, you'll get the hang of it. And drop a perpendicular from the axis. So this will give you the magnitude. So either one of them will give you the magnitude. Now we need to see how to get the direction also. Have a look at this page. Clear? Now how to get the direction. Now see. So to get the direction of torque, this is what we do. Assume that R bar is like a rod. So the vector which you're taking from the axis, assume it is a rod. And see the tendency of its rotation and use the right hand thumb rule. Meaning, look at this example. Listen to this carefully. If you got this, you got it. Let's say this is the force vector, this is the R bar. Meaning it's pretty intuitive kind of thing. Ask yourself, suppose if this was the rod and someone is applying force this way, will the rod go right side or left side? Itna to clear hai na? It goes to the right side, isn't it? So if the rod goes to the right side, that means this is rotating which way? Clockwise. That's it. You just need to ask yourself, is the rod going right or left? If it is going right, means it's a clockwise direction. Clockwise meaning minus k cap into the plane. So the torque direction is minus k cap. Is that making sense? Let's see one more example. Let's say this is your R bar. And let's say someone is applying force F this way. Now again ask yourself, how is the rod going? Is the rod going up or rod going down? Obvious, na down to nahi hai, it is going up. So if I know it is going up, meaning what direction is this? Anti-clockwise. Meaning the direction is plus k cap out of the plane. Torque direction is a pseudo vector. Is this making sense? So just imagine that R bar is like a rod, and when you apply the force, see which way the rod will try to rotate. That's your plane of rotation. Use right hand thumb rule, you'll get the torque direction. So this will give you the magnitudes, R perpendicular into F or R into F perpendicular. This will give you the direction. You know everything about the torque. Any doubt so far? Clear? Let's see few equations. You will get the hang of it. Can I turn the page? Nikhil, going ahead. Niharika, clear? Vihan, clear? Next thing. So we have an equilateral triangle, side A. So we have a force here, F1. We have a force here, F2. We have a force here, F3. We have a force here, F4. We have a force here, F5. So this F4 is exactly the midpoint. This F5 is making 45 degrees. O is the centroid. So these five forces are acting on this triangle. Find the torque due to these five forces about the centroid. Due to each force, I wanted to find the torque, magnitude, and direction. Try for a minute, then I'll show you one or two. If you're standing at the centroid, what is F1 ka torque? What is F2 ka torque? What is F3 ka torque? What is F4 ka torque? What is F5 ka torque? Torque due to each one of them. Try, take a minute or two. Let me show you one. See, first of all, you should know the triangle ka properties. In case you forgot, we have a problem. So if you have an equilateral triangle, the centroid will divide in the ratio of 2:1. So this will be 2/3 of the height, which is a by root 3. And this will be 1/3 of the height, which is a by 2 root 3. Don't forget these values. So this is your centroid here. What to do? Extend the force vector, drop the perpendicular. This is perpendicular. How much is this? A by root 3. What is the direction? So this F1, if you take this A by root 3 is a rod, it will rotate this way. So torque due to F1 will be A by root 3, perpendicular distance into F1, direction is minus K cap. Are you getting what I'm asking? You have to give me the magnitude and the direction. Similarly, if you have taken F2, extend the force vector, drop the perpendicular. So here the perpendicular is a by 2 root 3. So again, think about like this. So this a by 2 root 3 is your rod, and your F2 is acting like this. So which way will this rotate? This will rotate to the right side, means it will rotate this way. So torque due to F2 will be a by 2 root 3 into F2, direction is plus k cap. Is this making sense, everyone? The direction part and the magnitude. F3 is passing through the centroid, so luckily that is 0. Yes? Any doubts on 1, 2, 3? Anyone not clear with the magnitude, the direction, please ask, get them cleared. This is important. If you should know how to calculate torques. Without that, you can't go ahead in any problems later on. Clear? If you got that, can you try F4 and F5? I'll give you a minute. There are two techniques, remember, there's no need to take always R perpendicular. Try, I'll give you a minute or two. F4 and F5.
So can you show F3 1 minute?
F3 0 ना रे, passing through कुछ है ही नहीं उसमें.
अच्छा.
Case 1 ना, if you pass through axis torque 0 है. Okay, let's see. Let's see. For F4, now see it's a midpoint, right? So from here, if you draw a line, this is actually the bisector. This angle is 30 degrees. This is F4. So this angle is also 30 degrees. So I'll resolve this into components. F4 cos 30, F4 sin 30. And from here to here, this distance is a by 2 root 3. So this here I'm using R into F perpendicular. So torque due to F4 is perpendicular distance a by 2 root 3, perpendicular component F4 sin 30. Direction, you can see it is rotating this way. This F4 sin 30 will make you rotate this way, clockwise. That is minus k cap. Yes? What about F5? F5 is also similar. This is the centroid. This distance is a by 2 root 3. It is given 45. So this is F5 cos 45, F5 sin 45. This is going this way. So torque due to F5 will be perpendicular distance a by 2 root 3, F5 cos 45. Doesn't matter, cos sign is same, and the direction is plus k cap. Please check your magnitudes and the directions. Anyone not convinced with anything? 1, 2, 3, 4, 5. Anything that you're not clear, please ask. Magnitude, direction. Now, which one to take? You want to take R perpendicular into F, R into F perpendicular? Doesn't matter. Both will give you the answers. Sometimes when you do with one, you will realize you're getting stuck or it feels complex. Then divide the components. Luckily, there are only two ways to do so. Hit and trial will work. Is this clear, everyone? Let's see one more like this. That should make things more clear. Next thing. We have an hexagon, regular hexagon side A. This is point A. This is F1. This is F2. This is F3. This is F4. This is F5, which is passing through this point. Find the torque about A due to these five forces. A is the corner. Similar question, I just changed the shape and five forces are there. This is what I was saying. Depending on where you stand, you'll get different torques. So whenever they say find torque, your first question is, sir, about which axis? Without that, you can't go ahead with the problems. And again, I hope you guys remember in a regular hexagon, there are six equilateral triangles. Fine, I'll give you a minute more, then I'll show you all. It's more of a geometry. Like if you see, you should find the perpendicular distance and you're done, you'll get everything. Let's see. This is point A. This is your F1. Extend the force F1, drop the perpendicular. You can clearly see this is A, this is 30, this is A cos 30. So torque due to F1 is A cos 30, perpendicular distance. Magnitude is F1, direction, this will rotate this way, which is minus K cap. I am skipping the steps. So ask me if you're confused, but that's your answer for that. Similarly, if I take F2, extend the line, drop the perpendicular, this distance is A, this angle is 60 degree, and this is A, so this is A by 2. So torque due to F2 will be 3A by 2, F2, and F2 will rotate this way, up, so it is clockwise. This is F3, this is F3. This is also easy. If you extend the line and drop the perpendicular, you can clearly see this is 2 times A cos 30. Similarly, if you take this guy, F4, this thing passes through this. This is the perpendicular distance A. So torque due to F3 will be 2A cos 30. F3 is going towards the right side, meaning it's a clockwise direction, minus K cap. I'm just worried about the direction, so please ask me if I'm confused. A into F4, F4 is going up, so this rod, so this perpendicular distance is always the rod. You just need to see how will the rod rotate. It will rotate up, so that is plus K cap. The last one is a good one. So last one is an F5 passing through this corner. Anyone got that? That was the easiest one actually. If you see this angle is 30, so this angle is already 90 degrees. That means that is already the perpendicular distance A, isn't it? So torque due to F5 is A into F5, and if you can see F5 is going towards right side. That's your clockwise minus K cap. Please check your answers. Anyone not clear with the magnitude or the direction, anything, please ask. Clear, everyone? Next one. Next one. Great. Next thing. A force 2I minus J plus 3K acts at the origin. Find torque about the axis. Find the torque about the point A, which is 1 comma minus 2 comma 1. Get this. You have to use the vector form R cross F. How did you get zero, Record? What is R bar? I cap minus 2j cap plus k cap. If you have done that, you fell into the trap. Getting it? It's a simple mains question, but that's how they will trap you. That is the reason you need to be clear with the definition. Where is the force acting? Force is acting at the origin. Where is the axis? A is the axis. So what is R bar? R bar is a vector from the axis to the point where you applied the force. R bar is not the position vector. So R bar is AO bar. Are you getting it? That's what I wrote. R bar is not the position vector. It's a vector from the axis to the point where you're applying the force. So it's not OA bar, it is AO bar. So how much is that? It's minus I cap plus 2j cap minus k cap. So if you have taken I minus 2j plus k, you will get an answer with the overall minus sign. And that option will be there. That's it. That is the only trap in this question, nothing much. So you have to be careful about what is R bar. If you want to take that thing, then the question should be like this. The force is acting at point A, find the torque about the origin. Then it would have been OA bar. Then I hope you know how to do the cross product. I, J, K. R bar is -1, 2, -1. Force is 2, -1, 3. This is I cap 3, 2, 6, -1, 5. Minus J cap -3 plus 2 -1. J cap 1 -3. Right, we have. So we get 5i plus j minus 3k. Be careful with that. Not when Arya, you're right. Nee, Arya, you also got a minus sign. Somewhere it's messed up. Did I get it right? Check it out. So just be careful with that R bar thing. It's a simple mensural question. People do goof up and come. Some people are double lucky. They will write torque is equal to F cross R bar and they'll goof up R bar also. Minus minus cancel ho jayega, they'll get the right answer. I have seen people doing that also. Medical people are experts in that. They do two mistakes and they get right answers sometimes. Because their level of questions are easy. They get like straightforward questions most of the time. Clear with this? Easy one. So just based on definition. So be careful. R bar is not the position vector. Next thing. Rotational equilibrium. If the net torque acting on the system is 0, body is said to be in rotational equilibrium. Now, from the beginning, if you see, I was telling you, whenever I say torque, I should define the axis, right? Here I'm not telling you torque about which axis is 0. So the catch is this. Tell me one thing. Let's say if you say body is in equilibrium, that means, for example, let's say torque about an axis is not 0. That means it is rotating about that axis. And just now we proved today that if you rotate about one axis, you rotate about every other point, isn't it? That means if you are at rest in one frame, then you will be at rest in every frame. Is that making sense? Because omega must be same. So therefore, whenever they say rotational equilibrium, so for a body in rotational equilibrium, you need not ask about which point torque is 0. Torque about any axis is 0. So if a body is in rotational equilibrium, you can take torque about any axis and it will come to be 0. Because if you rotate about that axis, that means you're rotating about every other axis. Torque about any axis is 0. Then we define something called couple. Couple is torque due to equal and opposite forces. So again, torque due to a couple is independent of axis of rotation. So if someone asks you what is the torque due to the couple, it doesn't matter about which axis you take. So there are a few things which don't depend on axis of rotation. You could take anything and they will still work. Generally, axis of rotation is important. You need to keep asking. So how do you calculate torque due to a couple? So torque due to a couple is any one force. So there are two forces, right? Take any one force into distance between the forces. I'm sure you must have done something like this in school. Example, if you have 20 newtons, and let's say distance between them is 2 meters. Then the torque is 20 into 2, and you can look at the direction here. They are going clockwise, minus k cap. There, that is due to a couple. Clear, everyone? Next thing, we have something called a hinge. These are all terminologies. So hinge is basically, it's a point about which the body rotates. So this is how we represent a hinge. So it's basically a nut and bolt system. So the problem with that is because there's a nut and bolt, it is like this. Depending on where you're touching, if you touch here, the force will be that way. If you touch horizontally, force will be different. So the force will keep on changing every instant. So it becomes a little difficult to study. So what we do, whenever you draw an hinge in FBDs, we draw two perpendicular components. Nx and ny. Example, remember there's only one condition, they should be perpendicular. So I can take ny, nx, or I could have taken even ny, nx. It doesn't matter, both are right. The values will be different though, but if they ask you for hinge reaction, you'll get the same answer. Hinge reaction is the resultant of these two. This will be ny dash nx dash. So this will be root over ny square plus nx square. So in all FPDs, whenever you see a hinge, put nx, ny. That is because we don't know how the force is acting, so we take two perpendicular components. That's about the hinge. Yeah. Now, how do you solve these problems? Steps to solve equilibrium problems. Step one, choose your system, draw a free body diagram. with appropriate symbols. Step 2, apply F is equal to ma along two perpendicular directions. Now remember, this is an equilibrium, so A is 0 here. Then apply torque about the axis is 0. Now see, since it is an equilibrium, you can apply torque about the axis is 0. So preferably, right, choose an axis where max number of forces pass through. Yeah, this is just a choice there. The thing is, if you can take a point with maximum number of forces pass through, what will happen? Torque will be 0, no? So you will get the variables will decrease. So it becomes more easy to solve. You can take actually any axis, it works out. That's just a convenient thing. Then solve the equations. There. That's it. This is how you solve equilibrium problems. Here. Now let's see the problem. So let's say we have a rod here. You tied with two strings. This is a rod of length L, mass M. This string ka tension is T1, this string ka tension is T2. Find T1, T2. And this distance is 12 by 3. Now, if you just try to use Newton's second law, you'll get T1 plus T2 is mg and you're done. You won't get a second equation to solve. How do you do this? Let me help you with one. Listen, say. Step 1, choose your system. My system is the rod. And draw a free body diagram. T1, T2. Where will mg act for the rod? At the center of mass. So this was the thing I was teaching you from the beginning. Have to draw the forces properly. Then just make sure the distances properly. So this is L by 2. This is 2L by 3. Done. Step 2. Apply F is equal to MA in the horizontal and vertical direction. Horizontally, there is nothing. Vertically, T1 plus T2 is mg. Step 3. Apply torque about any axis. I can choose any point. I will choose this point A here. So torque about A. Now remember, I'm writing everything. So there are three forces: torque due to T1, torque due to T2, torque due to mg. There are three torques. Total is 0. Why? It is in equilibrium. Torque due to T1 is 0. Why? T1 is passing through axis. So I eliminated one variable actually. What is T2 ka torque? The perpendicular distance is this. How much? 2L by 3. Direction, it is rotating this way. So this is T2. 2L by 3. Direction is plus K cap. Mg ka torque is mg. Perpendicular distance L by 2. Direction is minus K cap. From here I get T2 is equal to 3 mg by 4. If T2 is 3 mg by 4, T1 is mg by 4. Are the steps clear, everyone? You can take torque about center mass also. Doesn't matter. You'll get the same answer. Clear, everyone? Got the steps. Let's see one more. This is theta. This is a rod, mass and length. And this is a string here. Gravity is there. Find tension and the hinge reaction. System is at rest. Hmm. Step 1. Write the forces. Now remember, whenever there's a hinge, put two hinge reactions, Ny and Nx. Mg will act at the center of mass of the rod. This is the tension there. So this component will be T cos theta. This component will be T sin theta. Resolve the forces into components. Vertical forces. Ny plus T sine theta is mg. Horizontally, Nx is equal to T cos theta. Now, which point is the best point to take torque? You can take any one. Answer will come. I'm getting it. I prefer the hinge. Why? Nx and y both are variables. Both will go off. So if you take torque about A, I need to take torque about Nx, torque due to Ny. I'm writing again everything. Later on, we will skip this step. Torque due to T sine theta. So when you're learning, it is better you write as detailed as possible T cos theta. So there are total 5 torques you have to calculate. But Nx will be 0, Ny will be 0, T cos theta will be 0 because T cos theta is also passing through A. Makes sense. So mg ka torque will be, remember, this is your perpendicular distance, L by 2. So mg ka torque is mg L by 2, direction minus k cap. T sine theta ka torque is T sine theta, perpendicular distance L plus k cap is equal to 0. There we get T is equal to mg by 2 sine theta. Once you got tension, substitute here. We'll get Nx is equal to mg by 2 cot theta. And Ny is equal to mg by 2. You get everything. Is this clear, everyone? Draw your FPD, write the forces, find torque, done. You'll get the answer. For now, things are not moving. Later on, when things move, we'll have few more steps to do. But idea was this. This is how it develops. Is this clear, everyone? So that's what I keep saying. Drawing your FBD properly takes care of most of the things. So let's see one more. Turn in the page. Let's say we have a beam balance here. Now this is a faulty beam balance. I'm pretty sure you must have seen this in a shop or something. So it's not exactly in the middle. Now in this beam balance, what happened? When you kept a mass M here, you required 9 kgs to balance. The same beam balance. Now you took that mass M and kept it on the right pan. Now you needed only 4 kgs to balance. You're getting it? See, if this was working properly, shouldn't you get same value on either side? Right? But this is not working properly. So when placed in left pan, it balances 9 kg. When placed in right pan, it balances 4 kg. Find the actual mass. Right, Purusha. Right, Adi. Now, see, if I try to derive this a general one, so when you draw the FBD, now see, let this distance be x, let this distance be y. This is mg, let this be m1g, let this be m2g, and let this be mg. So basically, this x and y won't change. It is faulty, but it is faulty on the same thing. So in the first case, when you balance the torque, it is mg into x is equal to m1g into y. We are taking torque about the this thing support. In the second case, it is m2g into x is equal to m1 mg into y. Two equations, divide them. You will get m by m2 is equal to m1 by m. It's a good result to remember. M is equal to root m1 m2. In our case, we get 6 kg. So that's your general result. So even with the faulty beam balance, you can still figure out the actual mass. Because if this had been a proper one, you would have got same reading on both the sides. Is that clear, everyone? Clear with this? So there. So that's the last one for the day. We'll wrap up with that. I'm not keeping that great. So next class, when we catch up, we will do more problems. We will do more little higher level problems on torque, right? And then we'll also do something called toppling. So, and after that, if time permits, we'll start off with the introduction of moment of inertia. Like I said, the three main points: torque, moment of inertia, and no slipping. You know these three things, 80% of the chapter is in your hands. The last 20% is angular momentum. That we will study specifically. It's a long chapter. This will take us more than a month, right? So once I finish off particular things, start solving parallelly. Right? Don't wait for the chapter to get over. It'll be too late by then. Okay, with that, we'll wrap up for the day. So next class, when we catch up, we will catch up on Tuesday at 5:40 as usual. So any doubts, anything, you can stay back and ask, or else you free to leave. So take care, stay safe.
Oh, sir.
Yeah.
So, like, I just had like a very small doubt. Like, what exactly is torque? Like, did we just define it for our own convenience? Something like
Okay,
that?
what is force? What is force according to you? Same thing, real logic. What you're saying, na, it is that only. It's like